you think about what I mean by a force, it's the means by which things interact with each other in the universe. So we're sitting on a chair now or standing on the floor or something. There are forces acting. Why don't you fall through the chair? Right, there's something stopping you falling through the chair. And that's electromagnetism, actually. There are two bits to it. One bit is that there are electrons, negatively charged things, in the atoms in your chair and in your arse. There's also a quantum mechanical effect, which is electrons don't like to be close to each other, which is called the exclusion principle. So you try and squash them closely. They repel each other, and they also try and avoid each other. And the combination of those is what makes stuff rigid, solid, right? Why is a brick wall solid? It's ultimately those effects. So it's forces. That's all there is. That's how you perceive the universe. It's why you stick together. So there's electromagnetism, which is a long-range force which is responsible for everything, actually, that we experience other than gravity. Light it's one of the strangest things in the universe, but one of the most useful, because it always travels at the same speed. It's what's called a constant of nature. How the thing moves that emits the light, or how the thing's moving that's going to receive the light seems to care about space and time, right? The fabric of the universe. It doesn't care about what emitted it or what received it. It just goes along. It's a perfect measuring instrument, because it always travels at the same speed. It doesn't matter if the thing that emitted it is flying away from you at 99% the speed of light. If it emits light towards you, the light comes at the speed of light and goes past you. Wow. So that allows you to measure distances, which is why it's useful, because a light year is the distance light travels in a year. Because it travels at the same speed, always, and nothing travels faster than light, it defines what's called the causal structure of the universe. So it tells us, if you have something that happens, can that something influence something else or not? Like, for example, if something happened, let's say there's a year light travel time. So anything that's further away than a light year for that time, for a year, within the space of a year, you can't communicate with it. It can't influence it. There can be no communication between the two, because you'd have to go faster than light to get from that place to the other event. And so light plays a fundamental role in relativity. It's not only useful, it actually defines what's called the causal structure of the universe. And that's where you get into, which we might talk about, black holes and things, because they're regions of space which even light can't escape. So light travels through space and time at this constant speed and divides it up into regions that can influence particular events and regions where events can't influence other events. And gravity tells you how all that curves and bends and warps, right? That's what and so in that sense, it determines the causal structure of the universe. It's gravity that tells you and warps space and tells you which regions can influence other regions and which can't. It's a really fascinating idea, these completely collapsed stars, the supermassive black holes, billions of times the mass of the sun at the centre of galaxies. The reason they're really interesting is because in the 70s, Stephen Hawking noticed that they do actually radiate. They have a temperature. They behave like anything else. And radiation comes off them. It's called Hawking radiation. And that ultimately makes them evaporate away in the very far future. And that caused absolute havoc in physics. And the reason it caused havoc is because people were worried about what happens when you throw something in. What happens to the information? So if I get this book and throw it into the black hole, does that information get destroyed? Or does it come back into the universe in the Hawking radiation eventually? Now, it's a fundamental part of all of science. If you know everything about the universe at some point, some time, then you can predict what's going to happen in the future, and you could predict what had happened in the past. Information is not destroyed. So you've got a very, very massive star, let's say 30, 40 times the mass of the sun. They hold themselves up against the pull of their own gravity by burning nuclear fuel, which releases energy, which creates a pressure, which holds them up. So they're in equilibrium, but ultimately they'll run out of nuclear fuel because of a finite size. And so they stop doing that and they collapse. And for these very massive things, nothing can stop them collapsing.